So thank you, everyone. Thank you for joining today. So today we have Rose, who is a PhD candidate at University of California, Berkeley. So today we'll be talking about her research paper, a high performance 48 to 8 volt multi-resonant switch capacitor converter for data center applications. Please go ahead, Rose. Please go ahead.
Thank you. Thanks for having me. I'm really excited about presenting to you guys and sharing with you some of my work on switch capacitor converters for data center applications. So today I'll be giving a little bit of background and motivation for this application with creating very efficient power supplies for data center applications. And then I'll go into the theory of the multi-resonant cascaded series parallel converter that I'll be presenting today, and also compare it to some other 6-to-1 conversion ratio topologies so that we can get a better idea of some of its benefits in comparison to existing work. I'll then go through a example prototype of a 6-to-1 converter, going over the hardware implementation, the experimental results, and comparing it with existing work, and then conclude the presentation. So data centers are becoming a huge fraction of total energy use when you think about it in terms of the fact that in 2018, global data center energy use represented 1% of total global electricity consumption. And 1% may seem small, but of the entire world global electricity consumption, that's actually quite a lot. As we are using more and more things like high-powered CPUs and GPUs and going towards cloud computing and AI processing, we have higher and higher demands for data center usage. And also the industry is shifting towards these so-called hyperscale high-power data centers, which are very large data center applications. So they may have very high power use compared to more traditional data center infrastructure. And as you can see in the graph on the right, hyperscale data centers are representing a larger and larger portion of the total data centers in the data centers installed. So being able to efficiently supply these data centers with power is becoming more and more important if we want to make sure that we are not going to drastically increase the electricity consumption required by this infrastructure. So there has been a shift in data centers in the last decade or so to move to a 40-volt server platform. So this is using a 48-volt bus to distribute power to the servers rather than the traditional lower voltage 12 voltage bus. And the reason for this move is that at high power, it's much easier to distribute the power to the servers at a higher voltage due to the reduction in conduction losses. So if you're distributing at 12 volts, you're going to have a higher I²R losses due to the higher current than you would at 48 volts. And especially as we are shifting towards data centers that consume more and more power at the server point of load, this is becoming a much more efficient way of delivering power by using this 48-volt bus. And the reason why they're choosing 48 versus maybe 70 or 100 volts is that there's a lot of legacy in the data center infrastructure that makes it easy to kind of switch to 48. So that's a voltage that's already present in telecom industry. It's considered a safe voltage level for human contact. So there's various safety standards that kind of vary from around 48 to 60 volts that say, any DC voltage below this can be handled in a much easier way than say 100 volts. And it's also easy to integrate with backup batteries. So if you're stacking lead acid batteries together, you can easily get around 48 volts. So looking at an example of one of these 48-volt data center power delivery systems, you can see that the energy is coming in from the grid, and then it's getting stepped down at the site substation and the power distribution unit. And there's also some rectification and power factor correction to make sure that we're not injecting any noise or large phase shifts back into the grid. And then we eventually get to this 48-volt bus. In order to actually power the servers, though, we have to step down this 48-volt bus. And a traditional, or traditional in the sense of being used very often in 48-volt data center power delivery architectures, that method is to step from 48 volts down to 12 volts. And the reason that 12 volts was picked, because that is kind of a legacy voltage. So a lot of distribution was already at 12 volts. So this allows you to use a lot of the same type of equipment. And so in this overall power system, or power delivery architecture, you'll step your 48-volt bus down to a lower voltage 12-volt bus. This may be unregulated or regulated depending on what the exact loads are. And then that 12-volt bus is going to be stepped down to a lower voltage. So a very common implementation is to use a hybrid switch-capacitor converter to step this 48-volt down to 12 volts. And that's because those types of converters can achieve very, very high efficiency. However, they're going to be fixed ratio, so it'll just be whatever the input is divided by 4, for example. So this first stage is not regulated, and the regulation is dependent on the second stage. And putting all the regulation on the second stage can make your first stage quite efficient. So your overall efficiency may be able to be higher than it would be if you had regulation at the first stage. But that is a design knob that people can use to optimize for their exact application. So then looking at the 12-volt to lower voltage or point of load voltage, this step is often implemented using some sort of buck topology, so that you can have regulation at the point of load, and you can also have a variable duty cycle to control exactly what voltage you're outputting. And so these types of topologies can be things like multi-phase buck converters, or other existing converters that are already on the market by industry. And so combining these first stage hybrid switch capacitor or fixed ratio converter with a second stage buck converter is a very common method for getting from your 48 volts down to your point of load. And so if we just also step back and take a little bit of a deeper look into this regulated versus unregulated, you can see that for a unregulated converter, your V out is going to be a set ratio of V in. So for example, if I'm using a 48-volt, 4-to-1 converter with 48-volt bus, I'll be getting 12 volts out, but only if my input is 48. If the input varies around 48, then my output will also vary. And the benefit of this is that it is easier to control. You don't need an extra feedback loop, but and you can also get higher efficiency. However, if you do need your intermediate bus voltage to be regulated, then this type of converter would not work for that. Whereas with a regulated converter, your V out can be kept at a specific value by doing something like a feedback control on the duty cycle as you're sensing the output voltage. And often these will have lower efficiency than a simple fixed ratio converter. So if we look though at the intermediate bus voltage, maybe 12 volts is not actually the best voltage for overall high system efficiency. And the reason for that is that your total 48 to point of load efficiency is going to be the efficiency of your intermediate bus converter stage times your efficiency of your buck stage. And so if we kind of do a survey of various off-the-shelf buck converters that can convert from anywhere from around 4 to 12 volts and output 1 volt, just for comparison's sake, we can see that the efficiency increases quite a lot as we decrease the input voltage of the buck stage. And that's kind of, you can think of it as the buck is stepping down less, so that conversion ratio is lower, and therefore its efficiency is higher. So we might be able to take advantage of this if we can reduce our intermediate bus voltage. So if we can operate our intermediate bus stage at around 6 to 8 volts instead of 12 volts, then now we're having the second stage efficiency that's in the in the low to mid 90s rather than the high 80s in terms of efficiency. And if we can use a very, very efficient first stage, such as a hybrid switch capacitor converter, then our overall system efficiency may be improved compared to a more traditional 12-volt intermediate bus solution. So that brings us to the design that I'll be presenting today, which is a multi-resonant cascaded series parallel converter. And it's kind of a long name, but I'll be going through each of the parts of that name of why that was chosen. And this is essentially a 6-to-1 converter designed for an 8-volt intermediate bus voltage. So if we look at this topology, we can kind of break it into two parts. So there's a 2-to-1 series step-down operation that happens during the first third of the switching cycle. And then there's a 3-to-1 parallel step-down operation that happens during the last 2/3 of the switching cycle. And I'll go through the switching states as well, and it'll make it a little bit clearer. But this series mode, parallel mode operation is where you get the series parallel of the name.
And Rose, would you like to take questions in between or at the end?
I'm happy to take them as they come up. Yeah.
Okay. Please go ahead. I will interrupt you if I see any questions in the chat.
Great, thank you. So then when we combine these two modes of operation over a whole switching cycle, we can get an overall 6-to-1 step-down operation. So if we look at the first 6th of the switching cycle, we can see that we have all of our capacitors connected in series. Therefore, it's a series mode operation. And we are charging C1, C2, C3 from our input voltage. And here, because we do have, if you look back at this circuit topology, you can see that the output of the switch capacitor converter has an inductor. And this inductor allows us to operate with soft charging, where we reduce the spikiness of the capacitor charge and discharge current. And we can essentially charge and discharge them with an almost constant current. And that reduces a lot of the charge distribution loss in switching these capacitors. So here I'm just modeling that currents through the inductor as effectively a current source. And so if you look at this converter switching state, you can see that if we wanted to talk about the resonant frequency of this converter, it would be simply based on the total effective capacitance and the inductance L. And so here, because our 3 capacitors are connected in series, our total effective capacitance is just going to be this reciprocal sum of C1, C2, and C3. And then our inductance, again, is just L. And so another thing to note is that we are operating in a resonant mode. So we can see that the current through the inductor and each of these capacitors is resonant, is this sort of half period of a sinusoid. So then if we switch to the next operating state, we are still in a series mode. So the C1, C2, and C3 are still connected in series. And that's reflected by the fact that our resonant frequency is still the same as before. And so this is why we have a series mode operation for the first 1/3 of the switching cycle. But now you can see that C1 is actually discharging into C2 and C3. So you can also see that by looking at the current for IC1 is now negative, whereas C2 and C3 are positive, as they're still being charged. And so then we enter the final mode of operation, which is the parallel mode. And so in this case, now we have C2 and C3 connected in parallel with the load, and they will be discharging. So now their current is negative, whereas C1 is completely disconnected, so no current is flowing through it. And now our resonant frequency is going to be this new effective capacitance times the inductance. And that new effective capacitance is just the parallel combination of C2 and C3. So this is where we get the multi-resonant part of the name, because there's multiple resonant frequencies, essentially multiple phases that this converter is operating in. So here we have 3 phases, and 2 of those are series and 1 is parallel. So if we kind of summarize this, we can look at this converter, and we can see that we do get this sort of resonant current waveform. And that can allow us to achieve zero current switching if we do switch exactly when that current hits zero. We can also look at the soft charging behavior of this converter. And if you do the calculation required by charge balance in C2 and C3 to say that, the amount of charge that they gain during the period, the first and second phases in series mode operation when they're charging has to be equal to the amount of charge that they lose during the last parallel mode phase, then you can come up with the limit that in order to achieve full soft charging, you need that C1 has to be at least greater than C over 6, where C2 and C3 are equal to C. So C2 and C3 have to have the same capacitance because they're operating in this parallel mode. And what's interesting, though, is that C1, if you look at this converter topology, that's actually the highest voltage rated capacitor. So you can see here that C1 must be rated for 3 V out, whereas C2 and C3 only are rated for V out. So even though C2 and C3 require a slightly higher capacitance, these are lower voltage rated capacitors. So you may still be able to get a very small form factor of total capacitance because you don't need to use very high voltage rated parts for C2 and C3, whereas C1 now does need to be rated for a bit higher voltage, but it has a much lower capacitance requirement. So this kind of balance between the two helps us maintain good smaller converter size. So we don't have to use like huge banks of very bulky capacitors for this topology.
Rose, thank you very much. We'll take one question because a lot of material was covered here. I think this is general question from Nachiketa. Will the distribution of power in a server stack become difficult due to reduction in intermediate voltage level from 12 volt to 8 volt?
Okay, great question. So I think if you look at a lot of various industry white papers and presentations at conferences like APEC, they're also looking at this problem. So they are already experimenting with some lower intermediate bus voltages. I don't think there would be any huge distribution problems because you're not distributing that 8 volts over a very, very large space. You're kind of just distributing it to maybe like one server rack or one small subsection of that data center. So it's not running through the entire data center. It's at they're designed to be like very concentrated around that point of load. So the idea is that you would distribute at 48 volts to as far as you can. And then once you're stepping down, you're stepping down right next to where the load is being consumed. So I think in terms of like 8 volts being lower than 12 volts, that wouldn't be an issue. But a main reason a lot of things are still at 12 volts is that I'll show in some later slides, is that these types of switch capacitor topologies, the number of components kind of increases a lot as you go up with higher conversion ratios. So a 2-to-1 or a 4-to-1 converter might have, on a like maybe an upper bound, like half as many components as a 6-to-1 or 8-to-1. So topologies, like there may not have been as many topologies that can produce these high conversion ratios in a low form factor. And so that's been kind of a limiting element.
Yeah, I had a question, Rose. In mode 3, when IC1 goes to 0, so both IC C2 and C3's current has been reversed. So can you just elaborate on mode 3? What is happening?
Sure. So essentially in the different modes, we're connecting the capacitors in different combinations and charging and discharging them. So C2 and C3 have been charging in mode 1 and mode 2. So they've either been charging from the input or they've been charging from C1. So then once you connect them in parallel in mode 3, they're now discharging into the load. And so that load current is actually getting split between the two capacitors. So the peak or the amplitude of that current is going to be different than it was during mode 1 and mode 2.
Thank you very much. Yeah, please go ahead.
Okay, so then just going back to this, to kind of hold this converter topology in your mind, you can see that if we look at all the switch and capacitor voltage ratings, we don't really have anything above 3 V out. So for an 8 volt output, that's about only around 24 volts, and it'll be higher if your input drifts a little higher, and lower if your input drifts lower. But it's not a huge demand on the switches. So we can compare this topology with some other 6-to-1 conversion ratio resonant switch capacitor topologies. So all of these other topologies that we're looking at are also operating in a resonant mode, where they could achieve soft charging. And if you look at the number of switches, the number of flying capacitors, so for the topology that I've just proposed, C1, C2, and C3 are considered flying capacitors. And just to go to this again, sorry for switching slides, but the reason that they're flying capacitors is essentially they don't have any node that's grounded. So C1, C2, and C3 can be reconfigured by all of the switching gating signals to hold different voltages, but they're not directly connected to ground. So if we look at this proposed topology, we can see that we have 10 switches and 3 flying capacitors, and then of course we have the 1 inductor at the output. And if we compare this with some other topologies, so a series parallel topology, which is actually kind of similar in operation, but would only be 2 phases of operation rather than the 3 that we see for this one, you can see that the switch number and number of flying capacitors is increased quite a bit. So now we need 16 switches and 5 flying capacitors, but still only 1 inductor. And you can do this type of analysis for several other topologies, including the switch tank or Dixon converter, which is same number of components as series parallel, or the flying capacitor multi-level converter, which has a slightly lower number of switches, but still a high number of flying capacitors. And one thing to point out with this comparison, though, is that the Dixon converter, this now requires 3 inductors. And so inductors, as you guys know, can add a lot of bulk to a topology. So depending on how you design this might take up a lot of volume to have 3 magnetic components, especially because these components, will have to carry a lot of current at the output depending on what your converter is rated for.
Rose, there's one more question.
Sure.
In the chat, it's great that the proposed topology reduces the number of switches and capacitors, but any comment about their voltage ratings?
Sure. So, and actually, I can show you a comparison of this. So this is a comparison of the switch and capacitor voltage ratings between all of the topologies. So you can see that compared to some other topologies, this one does have, it doesn't have the lowest switch voltage ratings, but it also doesn't have the highest. So here we have 4 switches that need to be rated at 3 V out, and then 2 switches that need to be rated at 2 V out, and 4 switches that need to be rated at V out. And I'll go over an actual hardware implementation where we can achieve this with normal low voltage MOSFETs. But if you compare this to other topologies, you can see that there is still some benefit here, in that we don't see like the very high switch voltage rating, for example, of the series parallel. And actually, the next couple slides will also go through this as well. We can look at some other metrics and kind of use them to compare. That will combine the fact that not only do we have less switches, but we also have average to low end of switch voltage. So when you look at the overall switch stress of the converter, it may be better than other ones, even if they maybe have lower absolute switch voltage ratings, they have more switches. So
when
go ahead.
Yeah, when you do the comparison, do you look at same conversion ratio, or when you're comparing topologies, do you focus on same conversion ratio, or how does that work, or only number of switches?
Right. So you can limit the comparison to the exact same conversion ratio, which I've done for this presentation. So actually, just to go into this, I can walk you through the comparison with several different converter topologies, and these are all for a 6-to-1 conversion ratio. So the two metrics that we can look at to kind of help us answer this question is something called passive volume. So that would be the total volume that's required due to your inductors and capacitors, and then also your switch test, which is based on the voltage and current that these switches have to handle. So you can think of this passive volume as kind of being a metric that is reflecting power density. So if you're requiring a very large passive volume, then your converter is probably not going to be able to convert a high power in a small area. So power density, again, is just a metric to basically say how many watts are you outputting divided by whatever the volume of your converter is. And you want that power density to be very, very high because then you can convert much higher power in a smaller space and reduce the footprint of the electronics and also reduce the footprint of the actual data center infrastructure. So so for passive volume, we want to decrease that to increase our power density. And for relative switch stress, you can think of this, since this relates the voltage and currents across the switches, this will be kind of holding a lot of information about things like switching and conduction loss. And so if we want to increase the efficiency of our converter, we would want lower switch stress. So we're essentially trying to operate as close to the origin of this graph as possible. And the actual method in which you calculate these parameters, I've included the citation for this paper that's also out of our group, and it walks you through exactly how to compare several different topologies using this method.
So what are the units, Rose, for X and Y axis?
So since these are normalized units, or normalized, so that's the relative passive volume is kind of normalized to the output power. So I think these ones are unitless, but the paper that I cited gives a lot more information on this. This is kind of a very detailed theoretical work. So there is a lot more information in the citation, but these are essentially just normalized. So we're just trying to compare, and as fair of a comparison as we can between the topologies.
Understood. Yeah.
So if we look at this, we can see that, sorry, the labels should have shown up, but we can see that if we take some of these converters that we looked at before, we can plot them on this chart. And so this yellow dot should be labeled Dixon, but you can see that this one has very low, effectively the theoretical minimum relative switch stress, but it has somewhat high passive volume. And that kind of reflects the fact that when we looked at that topology, it had low voltage ratings for the switches, but it had 3 inductors, so it has a large total passive volume. And this purple dot represents the series parallel converter. And so this one is kind of the opposite. So now we have essentially the theoretical minimum of passive volume, but we have higher switch stress. And so, sorry, these labels are not included, but
Rose, if you have the paper, you can just pull it up so that.
Oh, sure, yeah.
That will be.
1 second.
Yeah. Others, please post the questions in the chat so that we can take them at the end, so that we have them ready towards the end.
Okay. Apologize for that.
Or I have it here. Should I just share it? I have the paper with me.
I have the slide, so I can just share it. from my ECCE presentation. So sorry.
That's the great part about this. You pull up any document.
Sorry.
Okay.
Do you see the right slide? Or is
No,
it something else?
it's just a desktop. Yeah.
Okay. Sorry. Try that again. Okay, is this one the right one?
Yeah, yes.
Okay, so so I can walk through the same thing here. Okay, yeah. So as I said, if we look at the yellow, that corresponds to the Dixon. So we have high passive volume, low switch stress. And then if we look at the series parallel, we have high switch stress, low passive volume. So then if we populate this graph with some of the other topologies that we looked at, we can see that this work with the red star has a similar passive volume to the series parallel, which is very promising because that's theoretical minimum. And we have a slightly reduced switch stress. So we're still not as low as the Dixon, but we are, improved compared to the series parallel. So this topology at least shows several benefits in comparison with a series parallel topology. And then we can see that if we look at the FCML, that was another option. And here we're kind of moving more towards the origin, but at the trade-off of now having higher passive volume. And so the Dixon FCML, this work, and series parallel, these are all operated as resonant hybrid converters. And so if we compare it to a traditional buck topology, at the blue diamond, we can see that the buck is just way above these topologies in terms of both passive volume, and it's not higher than all of them, but it's on the higher end compared to the Dixon in terms of relative switch stress. So this is also kind of underlining the fact that we can get a lot of performance benefits by using these types of hybrid switch capacitor topologies. So with that, I'll switch back to the other presentation.
Yeah, sure. Good.
And then I'll introduce the actual hardware prototype that we built for ECC. Okay, is this the right screen?
Yes.
Great. Okay, so this hardware implementation was built for a 48 volt nominal input voltage with an expected swing of around 40 to 54 volts. So we also did experimental testing at these other input voltages. And the output voltage is nominally 8 volts, but again, this will vary in a fixed ratio with the input voltage. And the converter was tested up to 40 amps. So if you look at we show the top side and bottom side picture of the power conversion area of this converter. And so you can see that we're using several switches. So for those higher 3 Vout rated switches, because that voltage is around 24 volts nominally, we have to move up to a 40 volt silicon switch to be able to have enough headroom. Whereas with all of the other switches, we can just use 25 volts. And you can also see that the output switches that are in the output current conduction path, where we have a lot of high current, we've actually paralleled those. So that's to decrease the overall conduction loss of the converter at those higher currents. And then you can also see these capacitor banks of C1, C2, and C3 for those flying capacitors. And so just to give you a sense of scale, that the switch is so that 40 volt MOSFET, for example, by C1 is a 3 millimeter by 3 millimeter. So the capacitor area is actually quite small in terms of overall board area. And then one thing to note here is that we're using a 15 nanohenry inductor. And you can see that inductor, that basically is dictating the height of the entire converter volume. and also that's kind of a large part of the overall power conversion stage. So there is a lot that needs to be done to try to optimize the volume of this inductor while still maintaining very high output capability, and that's some ongoing work that we're looking at as well. And then the bottom side of the board shows the gate drive circuitry. So this was controlled using a bootstrap gate drive circuit, which essentially we can sort of connect several different gate drivers together using diodes and just power one chain of them. So that helps us get rid of a lot of things like LDOs and level shifters and isolators, and really helps compact the total area. So these two boxes that you see showing the top side and bottom side are including all of the power conversion stage components, with the exception of some external input and output filtering, as well as all of the driver circuitry. And then this converter was controlled just using a Texas Instruments C2000 series controller. So it's quite easy to generate those PWM signals, and it's not very complex control that's required. So then looking at the experimental waveforms, we can compare them with the theoretical waveforms, and we can see a couple differences between the two. So in the theoretical waveforms at the right, you can see that if you operate this converter exactly at resonance, you do achieve full zero current switching, because that current is hitting zero at every switch transition. Whereas in our converter, we actually operate the converter above resonance. And the reason for this is this helps us increase our overall efficiency by reducing the RMS current in the inductor. And we still are able to achieve quasi-zero current switching depending on the load current. So often the switch will transition at a somewhat low current. So we still get the benefit that we're not switching, for example, at a peak current of the sinusoid, but on the lower end. But we are sacrificing the full ZCS for the ability to reduce our RMS inductor current. And also by operating at above resonance, we no longer have to exactly match the exact resonance frequency of the series or of the effective capacitor network and the inductor. So we don't have to worry about part tolerances for those components. For example, capacitors could be 10 or 20% tolerance, and then you would have to sort of match that over the entire converter operation to be able to effectively track the resonant frequency if you were operating exactly at resonance. But now we've sort of removed that, and we don't care what that exact resonance is as long as we're operating above it. And you can also see by looking at the switch node that we do get some partial zero voltage switching, which is evident by the switch node going negative due to some body diode conduction. But that's only in a couple of the switches, and is not, we can't achieve that over every single switch over the entire load range. So then we can go through the efficiency curves and compare them at various input voltages. So this one is for 48 volts to 8 volts at 68 kilohertz switching frequency. So this is actually quite low compared to maybe some other topologies that you've seen. But this is not really an issue to be low, because this is just the first stage. So you would still have a second stage buck that, for example, could be operated at a much higher frequency if you needed that lower ripple and faster switching frequency directly at your point of load, because this is just an intermediate bus. So if we look at the efficiency for 48 volts, we've included both power stage efficiency as well as efficiency, including gate drive loss. This is done because sometimes in this area, people just report power stage efficiency if perhaps they haven't optimized their gate drive. So we like to include both so you can compare to whichever one better suits your application. And so you can see that we can achieve around 99.0% peak efficiency in terms of power stage, and then 97.1% at 40 amps. And then once we include gate drive loss, we still get very nice performance of 98.5% peak and 97% efficiency at full load. And so if we look at the efficiency over the entire operating voltage range at the low end of 40 volts, we still get pretty similar peak efficiency, and our full load efficiency has decreased somewhat. So you could think that for the same output current, so the same conduction losses, now you're outputting a lower output voltage. So you're outputting 6.7 volts instead of 8 volts. So your total output power will be less. So that conduction loss is representing a higher percentage of your total power, which is kind of leading to this lower full load efficiency. Whereas at the other end, when we operate at 54 volts with a 9-volt output, you can see that our full load efficiency is actually increased a little bit compared to the nominal 48-volt case. But again, our peak efficiency is still around this 99% without gate drive and 98.5 with gate drive.
So,
yeah.
we have a couple of questions.
Sure, yeah.
So ceramic capacitors are being used here. So
Right.
Their value might change due to voltage bias. So the
Right.
resonant frequency can also change. So how are
Right.
you dealing with this effect?
Sure. So this kind of comes into play with the fact that we're operating above resonance. So even though those values are changing, as long as we are above resonance, we don't really care what exact values those are, because we're not trying to exactly match that. So if you look at the capacitors that we use, these are, it doesn't say here, but I believe these are X5R or similar. So these are not C0G capacitors that have to be very big. We can just use standard MLCCs, and we don't actually care what the exact value is, as long as it's big enough. So it's more of like matching a margin than matching an exact value.
Yeah, it's more of a question of will your resonant frequency itself change? That's the question.
Oh, yes. So the actual resonant frequency would change depending on, because it's dependent on that effective capacitance. So it could change based on tolerances, but it wouldn't, it might slightly affect what the waveforms look like, but we haven't noticed any major problems with the tolerance. So we do tune the efficiency, as you can see at the various operating input voltages. We've slightly changed the switching frequency, and that's just based on kind of manually sweeping through and seeing what is most efficient. But it's not something where we really care or have to track it.
And can you go back to the PCB? There's one question related to the PCB.
Sure.
Can you comment on the thermal management of the prototype? What were the heat sinks used? Did you use PCB pores as heat sinks?
So I do have another slide that I can go to show the thermal image. So we don't use any heat sinks. We do just use fan cooling, like a benchtop CPU fan. And so you can see that the temperature doesn't really get above 60 degrees C even when we are at 40 amps output. And so we do have very heavy ounce copper. So this board is a 6-layer board. The outer layers are 4 ounce and the inner layer is 3 ounce. So we are trying to reduce conduction losses due to PCB resistance by upping the copper ounceage. We also do use PCB pores over the entire power conversion stage. So if you look at the layout of this board, there are large power planes that we're using to try to spread the heat. And this overall, this bounded box area is essentially just part of the overall board. So we have a larger board so that we can have connectors connecting to the power supplies and the efficiency measurement sensors. And so we do have like a larger ground plane for that whole PCB. But if you look at the thermal image, you can see here, the hottest part is that bounded box power conversion stage. And then you can see on the outside, there's, wires and cabling coming in, but it's much cooler. And if you look at the FETs that are getting hottest, these FETs are not actually the ground reference FETs. So we don't think too much heat conduction is happening due to the large ground plane over the entire area of the board. The really critical heat paths are more between the intermediate layers inside this bounded box area. And we haven't found that we need to use heat sinks for this topology at this output current and power. Simple fan cooling is enough blowing over the top of those switches that we can maintain, around 60 or lower.
So there's a question related to this image. How long was the board running at full load?
So the way that we test this is that we turn the board on and then we slowly ramp up the current. So it maybe, I don't know offhand how many minutes it was running exactly at 40 amps, but it'll be over the course of at least 10 minutes or so to get up to that current. So the board has been heating that entire time. And what's interesting is some industry manufacturers of similar types of converters, when they test the efficiency, they actually do a pulse testing. So they turn it on and measure the efficiency and then turn it off. So it hasn't been heating the whole time as you've been increasing the power. And so that's a measurement style that we're maybe looking to try to have more comparative data. But I think that would only get us to higher efficiency numbers because we are allowing the board to heat for a long time as we step up the power.
And coming to data centers, I believe you need a constant power, right? I don't think it varies that much. Does it vary based on, does the power requirement of a data center vary with respect to what kind of, like if they're training any huge data set, does the power consumption increase or is it constant?
So it does change depending on what you're actually doing. So I think sometimes you'll see stuff that's more centralized around the point of load. They'll show efficiency under like various read-write cycles. So the power consumption will change, but you're usually, like going to design for some nominal output power. So another thing to note is that even though this is, nominally 320 watts, these types of topologies can also be paralleled pretty easily. So you could get up to maybe 1,000 kilowatts by paralleling several of them together as needed, depending on the application.
We are on the previous slide.
Yeah. So then we can look also at something called load regulation, which is basically showing us how is our output voltage changing as a function of our current. So as we draw more current, that output voltage is kind of sagging due to increased, you can think of it as increased conduction losses or this increased loss in the converter at these higher currents. But due to the fact that this converter overall is quite efficient, this decrease is not very big. So if you look at the change in output voltage over the entire load space from 0 to 40 amps, that change is only about 234 millivolts, which represents 2.9% of V out. And again, this is for an unregulated converter. So it may not be important that output voltage is really staying at a rock hard, steady value. But it is nice that the inherent efficiency of the converter is helping us kind of maintain this very small delta V for a given input voltage. So again, this is for 48 volts to 8 volts. So you can see that output voltage is changing from around 8 volts to a little bit higher than 7.75. And then so we already kind of talked about the thermal characteristics of the board. So I'll move on. So we also tested load step behavior. And as this is a first stage converter for an unregulated intermediate bus voltage, the main thing that we're concerned about is, is this converter stable? Is it not going to just go off the rails when we rapidly increase or decrease the demanded current? So we did both a step up and a step down. So if you look at the picture on the left, this is from a 10 amp to 40 amp step at input voltage of 48 volts. And the blue line represents the demanded load current. So this goes from 10 to 40, whereas the pink line is representing our inductor current. So this is zoomed out, so you don't really see the full multi-resonant waveform, but you can see it sort of as a compressed waveform. And you can see that our inductor current, there is a little bit of an overshoot and then it settles. And the V out in yellow, you can see that there's a little bit of an undershoot before it settles to its newer, lower output voltage. And again, this is, the difference between 8 volts and maybe 7.75 volts for that output voltage. But overall, it's a quite steady, stable transition. So if you look at the inductor current within 100 microseconds, that's about maybe 200 microseconds. It's about normal. And so that's, good for this first stage. We don't need very, very fast regulation because this is not directly at the point of load. And then if you look at the graphic on the right, from a step down from 40 amps to 10 amps, you see similar kind of behavior. There's a little bit of an undershoot in the inductor current and a little bit, very small amount of overshoot for the output voltage. But again, these are stabilizing pretty quickly to their steady state values. And so this shows, a nice operation through these large step transitions. And then, so I just have some comparison with other work and summary slides. So I just wanted to stop again if there were any questions on any
One
of this.
question regarding switching. Did you face any issues with the, not too specific? Basically, they're asking, due to the switching, did you face any distortion in your waveform?
No, I don't think we saw any distortion with in our switching signals. So because we are switching at somewhat low frequency, it's pretty stable. There's a lot of control that you can have with using the C2000 microcontroller. So it's a pretty simple process to generate these gate signals.
They asked because you're going till 75 kilohertz. I think in one case 54 to 9 volts. Or maybe because of that. Okay. And I believe this was part of a product. So any EMI, EMC tests were done on the final board?
Oh, about EMI, EMC testing?
Yes.
Yeah. So we didn't do any of that for this board, just due to research constraints. Oh. But I think that these types of converters, have the potential for being pretty good with EMI and EMC, just because I think
topology, right, more than getting it certified as a product.
Sorry, can you say that again?
I think your focus was more on the topology, so I don't think you had
so that is something that we're looking, might look at more in the future. So this work is part of a larger data center power delivery architecture grant that we received from the Department of Energy and RPE. And so they're very interested in using this research work and actually implementing it in industry. So in that stage, we would have to look in more detail at the EMI and EMC. But we did not for this paper.
Please go.
Okay, thank you. So we can again look at a comparison topology with some other 6-to-1 conversion ratio converters that are already have been published or are actually for sale. So here we compare it with a Vicor topology. So that's an industry manufacturer that makes very high efficiency power supplies. And then as well with the EPC 9205 buck converter, which is an app note design from EPC, which is a GaN switch manufacturer. And then also compare it with the switch tank converter STC, which is more of a research topology and work. So if we look at this graph, we can see that we're graphing power density versus efficiency. So we're trying to kind of capture, both how efficient is it, but how much power can we get out of a small space. And so if we plot the power density at full load, and the efficiency at full load, as well as the power density at peak efficiency and peak as in relation to peak efficiency, we can get 2 points. So that's where we can get this sort of line that represents the overall performance of the converter in terms of power density and efficiency. So for example, the EPC 9205 buck converter, you can see that its peak power density is a little less than 1500 watts per cubic inch. And its peak efficiency is a little less than 95% efficient. And so we can use those two data points to graph this sort of operating area or line between connecting those two data sets. And then we can do the same for all of these different topologies. And as you can see, this work in blue has overall highest power density and close to the highest efficiency. So although the STC has slightly higher efficiency, we kind of have a better combination in terms of this graph of power density and efficiency, because we can achieve higher power density at essentially that same sort of efficiency. And again, these are all trade-offs that you will have to choose depending on your application. It's like the saying, there's no free lunch. Every time you try and increase efficiency, a lot of times that results in a decrease in power density. So this really is something where you're trying to turn up both knobs at the same time, but they're fighting against each other. But overall, the performance of this work is quite compelling when you compare it to the existing space. And we can achieve, very high peak efficiency of about 99% or 98.5%, including gate drive, while still achieving a nice full load efficiency of 97.1% without gate drive loss. And we can do that with a power density using our full load power of 2,230 watts per cubic inch. So this gives you kind of a sense of what other topologies and works are capable of. And then just to step back and put this into a little bit more context, our group has been working on several different hybrid switch capacitor topologies for data center applications. And so you can see this center boxed in red. This is the topology that I presented today. So the peak system efficiency of 98.5 and 2,230 watts per cubic inch for a 6-to-1 converter. And you can see that if you change that conversion ratio while using a lot of the same techniques, you can change your overall peak system efficiency and power density. So as you reduce your conversion ratio, you can get a little bit better performance. And if you increase your conversion ratio, you get a little worse performance. But overall, you can see that we've been able to create sort of a family of intermediate bus converters that you can pick and choose between depending on your actual application requirements. So maybe your application wants a higher intermediate bus converter, or maybe you can handle a lower intermediate bus converter, and you can pick the best topology for that application. And then, so just to conclude and summarize, that was able to achieve a high conversion ratio of 6-to-1 with less components compared to other resonant switch capacitor topologies. And there's several theoretical and practical benefits for implementing this type of topology. And we were able to show very nice efficiency and power density results for a 48 to 8 volt 6-to-1 hardware prototype. And I just also want to acknowledge that this work was sponsored by ARPE and DSEG. So we're very thankful for that support. And I'd like to open up to any and all questions that you may have.
Very and you have enough material for a journal, right? I was surprised they are putting for a conference. Is there any journal in the work session?
Oh, sorry, I couldn't hear that. My headphones are a little bad.
Yeah. Very good presentation. And is there any journal under review with so much work? Have you put it somewhere? Because there's so much expertise.
Yeah. So these three papers are representing that are cited here are for this 4-to-1, 6-to-1, 8-to-1 topology. And then I can also, if you're interested more just in the background of the hybrid switch cap work, these are a lot of good references. So I can share these with you, these slides as well. So the 6-to-1 topology that I presented has only been presented at ECCE, but we have some future work that we'd like to do with that. And then the 8-to-1 was presented at the last APEC. And then some of the 4-to-1 work was at the APEC before that. But yeah, I can, if anyone is interested in specific papers, I can also send those out.
Very good presentation. Very detailed. Thank you very much. I had one question regarding bootstrap diode. I'm not familiar with bootstrap diode. What is its functionality here?
Sure. So for the bootstrap gate drive circuitry.
Yeah, I think it is like I think I mentioned also. I think 23. Oh yeah. Go ahead.
Yeah. So this is an example of the bootstrap circuitry. So you can see that we are essentially connecting multiple gate drivers together with a sort of bootstrap diode to run it off of a single rail, this V power. And there's a lot more detailed work on this as well. And you can see the citations here. And I believe there's now, or at least in process, there may be a transaction paper for that based on this 2017 APEC paper on the bootstrap.
Yeah. Very good. And when it comes to, and all this with silicon switches, that is also great. You have achieved that efficiency with just silicon switches. That's also
right. So I think this is maybe somewhat outdated, but at these lower voltages of around 25 to 40 volts, the performance of silicon versus GaN is not as dramatically different as it is at higher voltages. So you can still achieve pretty low RDS on and gate charge and output or parasitic capacitance. And there is some benefits of working with silicon. We don't really experience like a lot of FET failures when we're actually operating the converter. It appears quite robust. So and also the price is much lower, so that helps from an industry standpoint as well.
And in all this work, when you had put it into conferences and journals, what was the common question asked by reviewers, or typically what were reviewers looking for during the review process?
So one thing that reviewers sometimes ask is, when you're at these higher efficiencies, they do want to know that you're measuring them correctly. So one interesting question is, people often ask what equipment you use to measure it, because if you're just using, the power supply readouts or a multimeter, it's very hard to accurately measure 99% efficiency. So we do use a Yokogawa power analyzer to get good accuracy on those numbers. So that's one area people often ask. Another common question is exactly how are you measuring the converter volume? So some people do this by summing up all of the major power conversion elements like switches, inductors, and capacitors. Some people do what we do of a box volume of just the conversion stage. Some groups try and make their overall board much more like industry ready. So they might pack in connectors in a much smaller form factors, and then they just use the entire board area. So overall, it's just very important to mention how you measure things and how you're calculating things, because another group may have a different method. And it's just best to be as transparent as possible about that so you can do fair comparisons.
Rose, very good work. Yeah, and also it presented really well. Thank you for giving the background, because the switch capacitor, I am also not that good with topology, but you explained it really well. And
Thank you.
even pitfalls, because we have few research students also in the audience. Any cautionary advice to them who are working in this area?
Sure. I guess I would say, like, to do a lot of simulation and calculation before you build it. But in general, it's good to make several different boards that you can test different variants on, because we do try to do a lot of optimization for efficiency. So you might be swapping out inductors and capacitors. So there's a lot of work that goes into getting those high efficiency numbers besides just soldering it and testing it. You're not really going to get the final design until you're actually at the bench doing a lot of measurements and optimization. So it's good not to ignore that, especially when you have deadlines like conferences or papers coming up, to kind of put that into your overall time frame and make sure you have enough time to really tune the system to get as high performance as you can, because a lot of times you might have one chance to present the topology, and if you don't get it to as high of a performance as it could be, it might not become, it might not get as much recognition as it maybe deserves, if, just based on the fact that your numbers are not as high as possible. So we try to spend a lot of time to get our numbers very high so that we can have good performance. And that does take a lot of work at the bench. Yeah.
What is the startup sequence? Is there a startup sequence, Rose, for your power?
No, there's no official really startup sequence. We do ramp up the voltage manually for the converter while the gate signals are already running. So that might be something to look into in the future, but as of now, we just do it manually.
Okay, yeah. Very good, Rose. Thank you very much for your time, and thank you. Because it's very early in the morning.
No worries.
Great work, and we hopefully will see more work from your lab. Very good work from your power lab, and thank you for your time.
Yeah, thank you for inviting me to give this talk. It was a lot of fun.
Thank you everyone for the presentation, and thank you for attending. So we'll end the talk. Thank you.
Thank you.